Hello everyone, in this video I will be going over some Mcat bonding problems. This is for the organic chemistry section, so if you're going to take the Mcat soon, this would be a very helpful video. Okay, let's start with the first question. And it says, which of the following correctly describes the hybridization and molecular geometry of the carbon atom in formaldehyde? Okay, so it's important to understand what hybridization is, and it is the merging of two electron orbitals. You might remember from general chemistry where you assigned the electric configuration for certain elements. So you would have, that 1s orbital, 2s, and then 2p. In this case, this is the merging of the 2s orbital and the 2p, and they both combine to create a hybrid. I think it's called 2sp3. And there's many reasons why hybridization takes place. One of them is to create stronger bonds as well as more equal bonds or equivalent bonds. Now, how I would solve this problem, I'm going to first draw out the molecule. So it's a carbon attached to an oxygen as well as two hydrogens. And I'm going to first count how many regions there are of electron density. And how I would do that is that triple bonds, double bonds, single bonds, and lone pairs, they all count as one region of electron density. So in this case, I have 1, 2, 3, 3. And this would make it sp2 hybridized. Sorry. How I did this was I put down all my letters, and there was 3 regions, so I'll go 1, 2, 3, which would make it sp2 hybridized. Okay, great. So for question 2, it says which bond is expected to be shortest. Now, you might be tempted to choose answer C, which is the triple bond, because usually bonds with more bonding would make it shorter, right? But D has a carbon single bonded to hydrogen. And because hydrogen is way smaller than the carbon atom, this would make this bond really short. And that would actually be our answer. D. Okay, great. So 3 says the sigma bond in an ethane molecule is formed by the overlap of which orbitals? Now, I'm going to do what I did before. I'm going to draw out the molecule. And I'm going to use my little trick. I'm going to put down 1 S letter and 3 P letters and count what are the areas of electron density. I have, for this carbon, I have 1, 2, 3, which would make it sp2 hybridized. And this one will be sp2 hybridized as well. Now, they are formed by the overlap of these two, which would make it A. Great. Okay, question 4 says, when two p orbitals combine constructively, the result is blank. A says a sigma anti-bonding orbital. It's important to note that sigma orbitals, it's when they overlap, so it looks something like this. There's two orbitals and they overlap like this. A pi bond, on the other hand, they form kind of, they're next to each other and they form like this. So in this case, two p orbitals, they're going to be pi. They're going to be pi bonding, not anti-bonding, because they just said that it was constructively combined. Okay, great. So for question 5, it says, which of the following structures demonstrates conjugation? Now, what is conjugation? Well, it is when you have a single and double bond alternation. It will look something like this. This molecule, on the other hand, when you have a double bond here and another one there, this is not one because it's not alternating. So it has to go single, double, right? Okay, so let's go through all of these molecules. I know for a fact it will not be A because you can't really see, but this methyl group is single bonded to a hydrogen, which disrupts the alternating pattern. Also for C, there's no double bonds in C, so that we can cross that out. And D, there's no alternating order. So that would make B our answer. It's kind of hard to see because you don't see the double bond to oxygen, but basically the molecule looks something like this. There's a double bond here, it's bonded to hydrogen, bonded to carbon, and then you have a double bond to oxygen, right? Okay, let's go to question 6. During the hydration of an alkyne, the central carbon atom changes hybridization state. What describes this change? Okay, so when an alkyne it goes under hydration, it turns into a ketone, as you can see here. So I'm gonna do our little trick. I'm gonna determine the hybridization of the central carbons. So in this case, this would be sp hybridized, because if I put down my letters, there are 2 areas of electron density, which makes it sp. In this molecule, on the other hand, there are 3 areas. So if I put down my letters, that is 1, 2, 3, which makes it sp2. So this went from sp to sp2, making our answer A. Great. Let's move on to question 7. 7 says, which of the following statements best describes bonding and anti-bonding orbitals? A says bonding orbitals are higher in energy than anti-bonding orbitals. This is incorrect because bonding orbitals are actually lower in energy because they are more stable. B says anti-bonding orbitals result from destructive interface of wave functions. This is correct. Option C says both bonding and anti-bonding orbitals increase stability. This is incorrect because anti-bonding actually makes it more unstable. And D says electrons in anti-bonding orbitals decrease bond order but increase stability. So it is true that it increases bond order, but this actually makes it more unstable. So that is incorrect. Okay. Question 8 says, which bond angle would you expect from the central atom in an sp3 hybridized system? Now I'm going to use our little trick. I'm going to put down the 4 letters, sp, p, and p. So an sp3 hybridized system, that is 1, 2, 3, 4. 4 areas of electron density. And if I go use the VSEPR theory diagram, I can tell that would make the shape tetrahedral, and that would make the bond angle 109.5, making it A. Okay, great. So in question 9, they said benzene's unusual stability can be explained by blank. A says localized double bonds within a ring. Now, this would be true if there was only one area of a localized double bond, like in ethene. If I draw out ethene, this pi bond will be localized because it's only shared in this one area. In benzene, on the other hand, it has multiple double bonds, and they are shared throughout the entire structure. It is not in one specific area. So this makes it delocalized. So we can cross out A. B said conjugated pi electrons that are delocalized in a cyclic structure. This is correct. We talked about this. C says sp3 hybridized carbons forming residence structures. If I take one of these carbon atoms here, I'm going to draw this a bit better for you. So if I take one of these carbons, I know it's attached to a hydrogen, and there is 1, 2, 3 areas of electron density, that would make it sp2, not sp3, making that incorrect. D says the overlap of sigma anti-bonding orbitals. This is incorrect because the thing that is making the benzene ring stable is actually the pi bonds because it's double bonding. Okay, we are at our last question, and it says the acetate the acetate ion has a negative charge that is delocalized between the two oxygen atoms. What is the hybridization of each oxygen atom? So because this negative charge is delocalized, I know that this is going to be a resonance structure. There's going to be resonance. So I'm going to draw our little resonance brackets, and it is alternating between these two structures. Now they're asking for the hybridization of each oxygen atom. So I'm going to use our trick and solve for the hybridization of all 4. Now I'm going to kind of speed this through, but if you do it, this one will be sp3. This will be, sorry, that will be sp2 actually, sp2. This is sp3. This is as well sp3, and this is sp2. Now, remember that these are alternating between these two structures, and it might be tempting to choose answer D, a mixture of sp2 and sp3, but this is incorrect. The correct answer will actually be B, and that is because these are resonance structures, and if one of the oxygen atoms had an sp3 hybridization, it will not be able to have resonance. It cannot become an sp2 in this case. If this went from sp3 to sp2, that would not be possible. Okay, and that is the end of the video. I hope you found this informative. If you have any questions, let me know, and have a beautiful day.